So first off, I want to apologize for not being able to attend the Arctic Science Summit Week in Russia this year. So unfortunately, my schedule didn't allow me to make it there to be with all of you at the end of May. And so instead, I'm recording this talk at the National Center for Atmospheric Research, which is my research home here in Boulder, Colorado. And I'm sure that you're all having a great time in Russia, and I really wish I could be there with you. Secondly, I'd really like to thank IASC for awarding me the IASC Medal. It's a really great honor. And again, I get choked up with these things. I'm really thankful and humbled to receive this award. So I'm going to stop talking about that because otherwise I'll get a little bit more teary. But it really is a great honor, and I really appreciate IASC for acknowledging me in my career in this way. So I'm going to be showing some work and some perspectives on predicting Arctic sea ice on different timescales. And I have here written seasons to centuries. It's really more seasons to multi-decadal timescales. But I'm going to show work and kind of perspectives on things that I've done through my career to try and understand predictability characteristics of sea ice on these different timescales, how internal variability plays a role on these different timescales, and what we can learn from climate models in terms of understanding the predictability characteristics of Arctic sea ice. And before I get started with the research in my talk, I just want to say that it really takes a village to understand the Arctic climate, how it's changing, climate variability and change in general. And I'm only showing a small set of the colleagues that I've worked with over the course of my career here. I've worked with a great number of people. There's probably people in the audience at the Arctic Science Summit Week that I've worked with and written papers with. I've chosen these people here because they're co-authors on the studies or leads on some of the studies that I'm going to be showing in this talk. And they're people that I've worked with over the whole course of my career. But there's many, many others, and I just want to note that I think one of the amazing things about the research that we do is that we get to work with really amazing people, really smart people, people that are very collaborative in nature. And I think for me, just thinking back on my career, having been awarded this medal, it's one of the things I find most rewarding in the course of my career, is to work with the people shown here and the many, many other people that I've been able to interact with over the course of my work. So in terms of the talk itself, I'm going to provide a little bit of background, and that background is really going to be on sea ice processes and how those sea ice processes are climate state dependent. And that has enormous implications for predicting sea ice on these different timescales. Then I'm going to show what some of the implications of that are for understanding sea ice loss on multi-decadal timescales, the role of internal variability in the midst of this very large anthropogenic change that's happening in the Arctic system. And then I'll follow that up with some work we've done recently looking at seasonal predictability of sea ice in the Arctic and how that seasonal predictability is likely to change because of the fact that these sea ice processes are climate state dependent. So as the climate warms, we melt sea ice, we thin sea ice. Predictability of sea ice on seasonal timescales is likely to change, and I'll share some results indicating that. And then I'll just end with some final thoughts. So when we're thinking about sea ice and how sea ice varies and changes over time, there's several processes in the sea ice system that are very directly dependent on the state of the climate. One of these is sea ice growth. And so I'm just showing a little schematic here on the bottom left. This would be sort of a thermodynamic piece of a sea ice model in a climate system model. And sea ice in the Arctic grows at the base of the ice. We have very little snow flooding. All the sea ice growth is really happening at the ice base. And that's dependent on a balance of fluxes at the base of the sea ice. And that balance of fluxes is strongly affected by the conduction of heat through the sea ice pack, which is affected by the vertical temperature gradients, which is strongly controlled by the sea ice thickness and varies as 1 over the sea ice thickness. So what this means is that thinner ice grows more rapidly. You can see that here in this result from an older paper by Bitz and Rowe, that as a function of ice thickness on the x-axis, ice thickness grows more rapidly in a thin ice cover. You can just think of this as thinner ice is less insulating, has larger ice growth. But that is nonlinear and particularly important in the thin end of the sea ice thickness distribution. And so this process works as a negative feedback on ice thickness, and that is ice thickness dependent. And that'll have implications for the results I'm going to show in terms of how sea ice varies and changes in the future. Another process in sea ice that is climate state dependent is the formation of open water over the summer melt season. So this is illustrated here from some results from an older paper back in 2006, where we showed that the efficiency of open water formation, so the amount of open water that you form over the melt season per centimeter of ice melt, is very strongly dependent on the ice thickness the previous winter. And again, this is nonlinear. So what this means is that as you thin the sea ice pack, you can have a much larger amount of open water formed over the melt season that has albedo feedback implications. And so that relationship is nonlinear with ice thickness, and it strongly affects projections of sea ice over multi-decadal timescales as you're thinning the sea ice and you allow much more open water to form over the melt season. So these sea ice processes are climate state dependent, and that's very important for how they play out and the impact that they have on our variability and change in sea ice in a warming climate. And I'll return to that throughout the talk. So how are we going to quantify that variability and change in the climate system in terms of sea ice? So it's very difficult to disentangle internal variability and a forced response or an anthropogenically driven change in the sea ice system just based on observations alone, because those observations are one realization. In the Arctic, that realization is pretty short. We only have really good observations over the modern satellite era. And of course, that change over time is a combination of internal variability and the forced response of the system. So I'm going to be using simulations from coupled climate models to quantify that internal variability and forced change. And for a lot of the work in the talk, I'm going to rely on this CESM large ensemble. This is 40 ensemble simulations from 1920 to 2100. All those simulations are subject to the same external forcing, same rising greenhouse gas concentrations in the atmosphere, same solar variability at the top of the atmosphere, et cetera. But they have very small perturbations in their initial state in 1920, just a round off level change in the air temperature in those simulations, but because of the chaotic nature of the system, those errors grow over time and those simulations diverge. So we can quantify the forced response, which is mostly anthropogenic in these simulations, as the ensemble mean of these 40 simulations. And we can quantify the internal variability as the variations around that ensemble mean. So I'll be showing results on that throughout the talk. I will note that in earlier instances, I also show some results from earlier versions of this climate model. And in that case, we don't have large ensembles. We have 8 ensemble members at most. And so it's a little bit less robust, kind of teasing out this internal variability and the forced response, but because we have fewer samples, only 8 members in that case. And I do want to note that while these models are biased, in terms of the sea ice simulated, in particular in this community Earth system model, the model simulates a really good mean sea ice state in the late 20th century. And I'm just showing a few indications of that here. This is the annual cycle of ice extent compared to observations. The ice thickness across the Arctic, which has a very good spatial pattern and a good mean thickness. the September extent time series compared to the observed record shown in red here. So you see sea ice loss occurring over the 20th and 21st centuries, and that ice loss is a little bit less rapid in general than the NSIDC satellite-based sea ice index. But the sea ice index, the observed changes, are actually within the envelope of what this model simulates across its ensemble members. And you see that indicated here on the lower right in terms of just the simulated 35-year trend histogram from the model in blue and the observed in red here, showing that the model can capture observed sea ice loss that's comparable to what we've seen in the observations. So I'm going to be using simulations from this model to quantify some of these things, and earlier variants of this model as well. Okay, so that gives some background on the fact that these climate sea ice processes are climate state dependent. So what implications does this have for the multi-decadal sea ice changes that we might expect in the future? Well, just going back to the 20th and 21st century projections of sea ice from this CESM large ensemble, I'm showing here on the upper left the ice extent in September. Upper right, this is ice thickness in January. It would look similar if I showed an annual average. And you can see that the model loses an enormous amount of sea ice over the 21st century and reaches near ice-free conditions in September by mid-century or so. It also has very rapid thinning associated with that. So of course there's a sea ice mass budget that makes up these changes that are occurring in the sea ice system. And that's what's shown here. This is changes in the sea ice mass budget in these climate model simulations, and I'm showing from 1980 out to 2050 here. And so you have increased melting leading to a loss of sea ice, but it's important to note that that's counteracted by increases in growth. So even though we have a rapidly warming climate in the Arctic, you get more sea ice growth, and that's because ice growth is ice thickness dependent. So even in a warming Arctic, you have increases in ice growth in the winter that counteract the loss of sea ice. You also have less transport of ice out of the Arctic basin. This is an Arctic basin ice mass budget, and that's just because the ice that's being transported out into the North Atlantic is thinner, so you're losing less mass through ice transport. Now it's important to note, so the total budget, which is shown in this black line here, which might be a little hard to see, is negative. You're still thinning sea ice in the Arctic, and you're thinning it very rapidly. But these processes in the sea ice system counteract that in terms of this increased ice growth. And it's important to know that that increase in ice growth is particularly true in areas of thin ice in the Arctic. And because of that, you get a dramatic change in the distribution of ice thickness within the Arctic as well. So that's what's shown here just for two different time periods, 1980 shown in red here, and 2020 shown in black. And what you see is that from these histograms of ice thickness for an Arctic region, 70 to 90 north, you basically, when you're thinning the ice pack over the early 21st century, what you're doing is losing the thick ice. You're not just shifting the distribution, you're actually changing it quite dramatically. And this has important implications for sea ice loss and sea ice variability in the Arctic, as I'll show. So you basically lose this thin end of the distribution and shift it into this 1.5 to 2 meter sort of thickness range. And this was noted in an earlier study by Bitz and Rowe when looking at the observations. So we're seeing these kinds of things also happening in the observed system. So these changes are occurring in the Arctic and have been observed. So that change in the distribution of sea ice actually has really important implications for ice area in the Arctic as well. So I'm showing and ice area variability in particular. So here again, and I've shown this plot previously, is the ice extent time series in September from these CESM large ensemble simulations, starting in 1920 and going out to 2100. The black line here is the ensemble mean across those simulations. So it's the average of those 40 ensemble members. And the blue shading shows the range around those ensemble simulations. Okay. And in red, I'm showing the observed record. That's, again, at the fast end of our distribution of ice loss, but generally within the kind of trends that our model simulates. So what about the internal variability in the sea ice system? So this shows the whole change, but there's some interesting things if you look at the range across the ensembles and how that changes over time. So I'm going to show that more directly by subtracting out the ensemble mean and just showing the anomalies about that ensemble mean. So that's what's shown here. This is the anomaly from the ensemble mean, which gives us a measure of the internal variability of the Arctic sea ice and how it's changing over time. And some interesting things come out when you look at it this way. First, the internal variability is quite stable over the 20th century. But as you move into the 21st century and the sea ice is thinning dramatically, you get also this dramatic increase in the internal variability of the sea ice. And we can quantify that a little bit more. So here, this figure on the left shows the 40 simulations. And then we can just look at the standard deviation of ice extent in September across those 40 simulations to more easily quantify that. So this is what's shown here. And you can again see what you can kind of distinguish by eye here, but now it's better quantified that, this ice extent variability in September grows. It peaks around 2020 or 2030 in these climate model simulations. And then it decreases to near zero as we essentially lose all the sea ice in September at the end of the 21st century. So this shows it as a function of time. On the lower panel here, I'm showing it as a function of thickness because thickness of the sea ice is a primary control on this. And so you see that here, when the standard deviation, the internal variability of the September sea ice cover is quite stable. You're sitting about 3-meter thick sea ice in the Arctic, averaged across the basin. As you thin that ice, this standard deviation grows. So the internal variability grows. And we can look into why. Oh, before I go on to looking into why, this shows the fact that this isn't just something that occurs in September. It actually occurs throughout the summer months, this increase in variability. But the month at which the time at which it peaks differs as you move throughout the summer. So I'm just showing that standard deviation, but now in August, July, and June is starting to grow at the end of the 21st century. So even once you lose all your September sea ice, you see that the variability in earlier months of the summer starts to grow until that sea ice is also lost by the end of the 21st century. So if we look into the reasons why we get this growth of variability in the sea ice, again, it comes back to the ice thickness. And so we can think of the sea ice as in the Arctic of being made up of regions that always melt out. The ice is thin. Every summer, that area is going to melt out. There are regions in the Arctic that never melt out. Typically, that ice is too thick, never melts out. And so those regions don't impact the variability of the September sea ice extent. But then there are these regions where you have highly variable meltout. And so I'm showing the distribution of sea ice thickness in those regions. In the 1980 climate in red, the 2020 climate in black. And what you see is that most of the sea ice that's in this highly variable meltout regime is in this 1.5 to 2 meter thick ice distribution of sea ice thickness. And as we saw previously, the sea ice is thinning such that you're losing this thick ice, which was much more stable in terms of its never melting out and never contributing to ice area variability in the summer. And you're moving that into this 1.5 to 2 meter thick portion of the distribution where you have this possibility of meltout just depending on the weather conditions from one year to the next. And whether or not you get a particularly warm year, you'll melt out the sea ice in that domain. And if you have a particularly cold year, you might not. So these shifts in the distribution of the thickness of the sea ice, which are dependent on the fact that ice growth is ice thickness dependent, also then have implications for the variability of sea ice in the September and summer months more generally. So how do these different factors, the fact that we have changes in the distribution of the thickness of sea ice, changes in the variability of sea ice, we have this increased open water formation efficiency as the ice thins, how do they conspire to affect the transient sea ice response in the summer in response to rising greenhouse gases? So we were asking these questions back in 2006 or 2005 when we were working on this study. And we were looking at model simulations from an earlier version of the CESM model. So these are simulations from the Community Climate System Model, version 3. So this shows the time series from that model from 1950 to 2006 here, when we published this study, compared to the observed record that we had at that time. And looking at this, we thought the model's actually doing a quite reasonable job. We're getting sea ice loss that's a little bit different than the exact character of what's been observed, but more or less around the same magnitude. So we were pretty happy with this. And then when we looked into the future, we found that there were these instances of incredibly rapid sea ice loss that could occur. So this simulation in particular goes from about 6 million square kilometers of sea ice to 1.5 million square kilometers over a decade. So at the time that we published this study in 2006, this was shocking. And we actually thought perhaps there was just something really weird in this one particular climate model simulation. So we looked at the 7 other ensemble members that we had from this model, and we found that across those 8 simulations, this was something that occurred quite regularly. We actually have 10 events across 8 simulations. These instances of rapid sea ice loss were something that perhaps we should expect to occur. So this particular simulation shown in black was a little bit different in that the rapid ice loss event was longer lived. It lasted about a decade. Many of these other events lasted more like 5 years, but they all had rates of change that were much larger than anything that we'd observed. The next year, the sea ice dropped dramatically. So we were really lucky at the timing of this paper. In that September 2007, we lost an enormous amount of sea ice in the Arctic. And I think this took the Arctic research community by surprise. We were all quite shocked. But you could argue that since this paper was published, we've actually seen a rapid ice loss event of the type that this model was simulating before it occurred. So we can look into the factors that drive these kinds of rapid ice loss events. And we did find that there were common factors across these 10 different events that we identified. These events all had a rapid thinning, kind of a pulse-like increased rate of thinning over the course of their events. And I'm showing this here just for that one particular simulation. But that thinning was not particularly dramatic compared to earlier time periods, even in the early 20th century. So there was something different about this thinning compared to earlier events in the record. We also found in our climate model that these periods of thinning, these rapid thinning events, were often preceded by increasing heat transport from the ocean into the Arctic from the North Atlantic. And so we had this overall increase in ocean heat transport to the Arctic. We also had these sort of pulses that appeared to precede these thinning events and these rapid ice loss events. And we found that those were related to wind forcing, and in particular, the North Atlantic oscillation in the model. So they looked like those pulses were internally driven variability. So the reason that these thinning events, of course, had a larger impact on the sea ice area in the summer was because of this increased efficiency of open water production for a given ice melt rate as the ice thins. And so when you're sitting out here in a 3 to 4 meter thick range, if you melt a lot of sea ice over a 5-year period, you're not going to have a very large impact on open water formation over the melt season and the resulting September ice area. Whereas when you're sitting here more at a meter, meter and a half, a thinning event is going to drive a very large change in the September sea ice extent. So we found that in terms of these rapid ice loss events, which have come to be known as RILES, there were 3 different ingredients that were important. We needed a thinning of the sea ice to these much more vulnerable conditions where processes like this could kick in. We needed a kick that was provided by internal variability. In this case, in these model simulations, that was ocean heat transport to the Arctic. We've found since then that many other things can provide that sort of a kick. And we also needed positive feedbacks, an albedo feedback associated with this ice area loss that accelerated the retreat. So there were 3 things involved. And in later studies, we tried to look at whether this resulted from threshold behavior. Was this a tipping point? And we found very little evidence that there was any sort of tipping point behavior, threshold behavior that led to these instances of rapid ice loss. And instead, they resulted from this very strong anthropogenic change that was reinforced by this growing internal variability in the September sea ice cover. And those 2 things together led to these rapid loss events. So that's where we were in 2006, and of course it's been a long time since then. And we've learned a lot more about the role of changing intrinsic variability in the sea ice in the midst of this forced change. And of course, there's a whole community that's been working on this problem since that time. I'm only going to show a few results from some studies I've been involved in. I think we have much more evidence that the observed ice loss in the Arctic has likely been reinforced by internal variability. This comes from a paper led by Julian Struve back in 2007, but many more recent studies have also shown that observed ice loss is very likely driven by or enhanced by internal variability in the Arctic. And some of them tying it down to the actual atmospheric circulation patterns and showing that models can simulate those kinds of processes. We've also learned that even in a warming climate into the 21st century, we can see decadal increases in sea ice in the summer. So this shows a result from a paper led by Jennifer Kay back in 2011. This is the histogram of decadal trends in sea ice for different time periods, a pre-industrial climate in black, a late 20th century climate in blue, and this early 21st century climate in red. And you can see that while the distribution shifts to negative values, you still have a lot of increasing trends occurring on a decadal timescale, even in this rapidly warming Arctic climate. And that's because the internal variability increases and it can counteract the forced change. Now, of course, if you look on longer timescales, multi-decadal timescales, you see this happening less and less. And by 2050, mid-21st century or so, these models reach ice-free conditions in September and don't recover from that as the greenhouse gas concentrations continue to rise. But we also find that if we're trying to look at the actual predictability of the timing of those ice-free conditions, it's nearly impossible to within something like a 20-year window. And this was shown in this study led by Alexandra Yan back in 2016, where she looked at predictability of the timing of September ice-free conditions in the Arctic. So she's showing a histogram here. The blue bars here are from the CESM large ensemble. So they're just a measure of the internal variability across those simulations. And you can see that while all of these simulations are subject to the same rising greenhouse gas concentrations in the atmosphere, the time at which they reach ice-free conditions in the Arctic differs by about 20 years. So there's an irreducible uncertainty in terms of the predictability of the first year at which ice-free conditions result in the Arctic of about 20 years, just due to internal variability. The green bars here are from a lower emission forcing scenario. There's actually quite a few less simulations that make up this histogram, but for this lower emission forcing scenario, while you can see it shifts to later in the decade, which they reach ice-free conditions, there's still this very large uncertainty in terms of when that will occur because of internal variability. So I think we have a much better appreciation of the fact that internal variability is growing in terms of September ice extent and earlier months in the summer as well, as we move into this rapidly warming and thinning Arctic state. And that has implications for many, many different aspects of Arctic change on these decadal and multi-decadal timescales. So for the remainder of my talk, I'm going to show some results that suggest that this also has really important implications for forecasting sea ice on seasonal timescales. So I'm now looking at this predictability of the first kind. So the work that I've shown up till now is really more this boundary value forcing problem. The fact that greenhouse gases in the atmosphere are rising, that influences the climate system, and that provides us with predictability. For the rest of the talk, I'm going to be focusing more on this initial value predictability. And this is illustrated nicely here in this schematic that's been adapted from Brandstetter and Tang, where you see these initialized predictions. They all start with very similar initial states, but then because there's errors in those initial states and the system is chaotic, those errors grow over time and you start to lose predictability. And at some point, the prediction from those simulations doesn't differ from what you'd get just based on the boundary forcing. So when the spread across a set of ensemble simulations is comparable to the spread that you would get just looking at climatology, your predictability is lost. So I'm going to look at this in the sea ice system, but I'm also going to ask the question of whether those initial value predictability characteristics might change in a warming climate. And of course, because we've seen that sea ice processes are climate state dependent, there's some reason to believe that they should. So I'm doing this by looking at a set of simulations that we've performed that uses the community Earth system model. And these simulations are in this perfect model framework. So basically, I'm using the model to try and predict the model. And what I've done is run for every decade from 1980 to 2030 a set of initialized prediction simulations. They're all initialized on January 1st. They use initial states from the climate model. So we have basically a perfect knowledge of the initial states. And then we run them forward for 1 year. Now, because we know that at each decade we have a range of possibilities because of internal variability, we actually do 4 different simulations at each decade, 4 different sets of ensemble simulations at each decade. So that's what's illustrated here. These shows 4 of these prediction ensembles, and now this is just from the 1980 ensemble set. I'm showing the Arctic Ocean ice volume here. So all of these are initialized on January 1st with nearly identical initial states. Their ice conditions are actually perfectly known. There's just a small error in their air temperature across those ensemble members. That error will grow over time. And you see for the Arctic Ocean ice volume, that starts to lead to a spread across these ensemble simulations after a couple months. And then they continue to spread as we move into time. So we can quantify that spread across the ensemble simulations, these prediction ensembles, and compare it to the spread that we get just due to internal variability from our CESM large ensemble. So that's what's shown here. This is the variance of ice volume in these prediction ensembles as a function of day of year, so initialized on January 1st, moving through time. And then this is what we get from internal variability. So you can see that compared to internal variability, these prediction ensembles stay fairly tightly grouped in terms of their ice volume or ice thickness in the Arctic. And this suggests that ice volume is predictable. It has high predictability for a year. It's better to take one of these initialized predictions as what the state, what you expect the state will be, than to pick something from the climatology of our control simulation in this case, or nature in a less idealized case. So this shows it for ice volume. What about ice area, which in some cases is a more important stakeholder value? Many people are interested in marine access in the Arctic now, so knowing what the ice area is going to be in summer months is particularly important. So I'm showing this here. This is very similar in its character to the previous plot. This is the variance across those ensemble simulations, the prediction ensemble shown in blue, and then due to internal variability in red. And this is for 1980, the ice area in the Arctic Basin, starting now in June and running through December. And you can see actually something quite different. These two lines lie directly on top of each other. So what this suggests is that there's no predictability for the ice area in summer months from these January 1st initialized predictions. You might as well just take something from the uninitialized simulations that's indicated by the red line. There's no predictability for summer ice area, according to this. What if we look at these later decades? Well, what we find is that we see an emerging predictability of sea ice on these kind of seasonal timescales. And so what you find is that in 1990, 2000, up till 2030, which is shown on this lower right panel, the difference between the internal variability shown in red and this prediction ensemble in blue, you start to be able to distinguish them, suggesting that there is predictability in sea ice on these timescales if you look at these warmer decades. And that predictability, we can quantify it, and we actually can show that it's particularly large in the 2010 time period. This is in part because the internal variability in the sea ice is growing, right? So it's not just, the difference between this 1980 state is more because the red line is increasing. But of course, if you're living in a 2010 climate, you're living in this climate of the red line. You're living in this very highly variable summertime sea ice area. And if you can reduce that and predict what those conditions are going to be, even initializing forecasts on January 1st, that's really important. So we can look at the processes that lead to this loss of predictability. Before I go there, I'll just show that this is also true if we look at ice concentration across the Arctic, which is what is averaged into those hemispheric averages. And again, this 2010 time period stands out as being highly predictable. And that's particularly true, or that's also true if you just look at the region where there's high ice variability. So in this case, darker colors, the darker blue colors, as a measure of predictability, are areas where there's higher predictability in the September ice concentration. So if we look at the processes that lead to these changes in predictability, we can go back to some previous work that shows that ice thickness is a very important predictor of ice area the following summer. And so we can think of the loss of predictability in sea ice as being related to the fact that these ice thickness errors grow from their initialized state on January 1st. And this is just shown for one set of those ensemble simulations now. And so that error will grow over time. And by early summer, that range of ice thickness errors will have very strong implications for the September sea ice cover. So the first aspect here is this growth of ice thickness errors from the initialized state. The second component of this loss of predictability is that these ice thickness errors have implications for meltout over the summer months. We can quantify that by just looking at the regression of the September ice area on the y-axis here with the July ice volume. This is shown just for these these predictions initialized in the year 2000. And so you can see that, if the end of July you have quite thick sea ice, you're going to lose less of it over the summer months and retain a larger September ice area. So these two factors are important in terms of the loss of predictability. And we can quantify them for these different climate states. So what I'm showing here is the growth of ice thickness errors or anomalies from the initialized state in January and then through time for months up until September. Warmer colors here are for the warmer decades. So what you see is that in these colder decades at the end of the 20th century, you have this very large growth of ice thickness errors. That growth of ice thickness errors decreases in the warming climate. And that's because those ice thickness errors are driven by differences in thickness that can occur from weather affecting what's happening in the spring months. But because you have this strong relationship between ice thickness and ice growth rate, if you're in a thinner ice regime, those ice thickness errors will be quickly damped because your ice will grow more if you thin a little bit, right? So you have a stronger damping of ice thickness anomalies in the warmer climate because of the thinner ice. So that how quickly those ice thickness errors grow is very strongly climate dependent and related to that relationship between ice thickness and ice growth rates. So this would suggest, this ice thickness error growth, that you'd actually have more predictability in the warmer climate. But this second aspect of the loss of predictability is larger in the warmer climate. So while these ice thickness errors are smaller at the beginning of the melt season, they have a much larger impact on the melt out of sea ice over the summer months. And so they have much larger sensitivity of the summertime melt out to these ice thickness variations. So I'm quantifying that here with the regression of September ice area on these ice thickness anomalies as a function of time. And so you see that it grows rapidly when the ice thins and is quite large for these later decades. And this is related to also that growth of September ice area variability in the warming climate. So what this means is that this 2010 time period has the highest predictability because it sort of sits in this Goldilocks zone in a sense. And so it has a modest growth of ice thickness errors compared to earlier decades. But it also has a modest impact of those ice thickness errors on meltout over the summer. And so because of that, there's sort of this sweet spot for predictability of the summertime sea ice area that's because of the ice thickness that's present in this 2010 climate state and how it affects these different processes. So we've seen that these climate state dependent ice processes can affect predictions on seasonal timescales and also on multi-decadal timescales. So some final thoughts. So again, these sea ice processes, the related feedbacks, related internal variability, these things are climate state dependent for sea ice, and they're in particular dependent on the thickness of sea ice in the Arctic and the distribution of that thickness within the Arctic as well. And this affects the multi-decadal sea ice loss. It leads to things like instances of rapid sea ice loss events. It also leads to changes in the internal variability of sea ice as we move into a warmer climate state. It also has implications for the seasonal predictability of sea ice and the fact that that seasonal predictability and the characteristics of it are likely to change in a warming climate. It also has implications for understanding differences across models. So because these models, sea ice loss and variability in the 21st century, are very strongly related to their mean sea ice states. And so a very nice paper by Francois Massenet and colleagues that I wasn't involved in has looked at this in terms of trying to understand differences across climate models and their projections of sea ice loss. And so all of this means that simulating a good present-day sea ice state is really important if we're going to predict sea ice on these various timescales and have reliable predictions. So all the work that I've shown has really focused on model simulations and using models to understand the Arctic system. I've also been involved a lot in trying to think of better ways to synthesize observations and models. And Don Perovich and I have been thinking about this quite a bit over the years. And I really think that we need a greater synthesis of observations and models in order to understand and alleviate the biases that we have in these models and to improve our predictions. Because of that, we also need a better collaboration and integration of scientists primarily working in observing communities and primarily working in modeling communities. And I think that's something that things like IASC, the International Arctic Science Committee, is at the forefront of trying to figure out how we work together to advance the science. So with that, unfortunately, I can't take questions from those of you in Russia because this is not a live presentation. But I would very much welcome any questions, thoughts you have. Here's my contact information. Please feel free to reach out to me by email, by phone, at the next meeting we bump into each other at. And I really appreciate your time. And again, thank you so much for awarding me this honor. And I wanted also to leave up a list of references because I think the work I've shown here and all the work that we build on, we're building on. There's an enormous amount of work that has come before. And I've shown information from many different studies throughout the course of this talk. And I think, it's important to realize and recognize that, this is something that we all do together to advance the field and make progress in terms of understanding this rapidly changing climate that we're living in. So thank you.